So in this video, we talk about expression of instruction. First of all, we use three address ISA. So let's see how to evaluate an infix expression using different instruction format. With a three address ISA, for example, in a mainframe, the infix expression of z equal x multiply y plus w multiply u gonna be represent something like this. That's a multiply r1 x y. So basically this expression saying that now we perform the multiplication of x and y, and the information, the result gonna be stored into the register r1. The second one gonna perform multiply r2 w and u, so it means the multiplication of w and u gonna be stored into the register r2, and the last expression gonna be performed by add z r1 r2, so it means the result in r1 and r2 gonna be added together and gonna be stored to the variable z. Okay, so this program with the three address ISA gonna be have only three instructions. Okay. Now, if we use two address ISA, for example, that's the common ISA of Intel, Motorola, and so on. Okay, the infix expression z equal x multiply y plus w multiply u gonna be expressed in the following way. So the first of all, we have the load r1 x. So basically this instruction saying that we load the variable or value of the variable x to the register r1, then we do multiply r1 y. So this saying that we're gonna perform the multiplication of the register r1 with y, and then the result gonna be stored back into r1. The next instruction saying that load r2w, so it means the value of variable w gonna be loaded into the register r2, and then multiply r2 u. This means we multiply the value of u to the value in the register r2, and gonna be the result gonna be stored back into the register r2. And the next one gonna be add r2 r1 r2, is mean we take the value of r1 and r2 add together and we store into the register r1. Then the last instruction saying that store z r1, is mean you take the value in the register r1 and store that value to the variable z. Okay, so we can see that this one with the two address ISA, we see has more instruction compared with the three address ISA as we saw before. So we also can note that one address ISA usually require one operand to be a register. That's the implicitly understanding. Okay, we can see a example soon. Now, if we're using one address ISA, let's say so basically the one address ISA that the Murray architecture as we discussed before. So the infix expression z equal x times y plus w times u gonna be represented as follow. So first of all, we load x. So this saying that the load the value of the variable x to the register, that's the AC accumulator, and then we do multiply y. So it means we take the value of variable y time with the value, or multiply with the value in the AC or accumulator, and then the result gonna be stored back into the accumulator. Then we do the store temp. It means we store the value in the accumulator to the variable temp. Okay. Then we perform load w. It means we load the value of the variable w to the AC. So now we overwriting the value of W to the AC. So now the AC store the value of the W. Then we perform multiply U, so it means we take the value of U, multiply with the value in the AC, and store the value back into the AC. Next one, we perform add temp. It means we take the value of temp variable right here, add with the value in the AC right now, and the value in the sum gonna be stored back into the AC. And the last instruction is that store Z. It means you take the value in the AC and store into the variable Z. Okay, so that the instruction using on address ISA. The next one, we see how to use stack ISA to perform or evaluate the postfix expression. So the postfix expression Z equal X, Y multiplication, W, U multiplication, and addition. So the instruction for this postfix expression can be look like this. Push X, so it means you scan X and you push it onto the stack, and then push Y onto the stack, and then you have the multiplication right here. So it means you take the value of X and Y and you multiply together, and the result gonna be pushed back onto the stack. Okay. Next one, we push W and we push U, and then we multiply. So the value of W and U gonna be performed by multiplying together, and we're gonna push back the result of multiplication W and U onto the stack. So now we have the at the bottom we have the multiplication of X and Y, and on top we have the multiplication of W and U. The next one, we have the add, and now we have the add. We have gonna pop up the value of the multiplication of X and Y and the multiplication of W and U, and we add them together. So we have the result of the addition between the multiplication XY with the multiplication of WU, and the sum gonna be pushed back onto the stack. So now the stack have only the result of the X times Y plus with the W times U. Okay, so so once we perform the addition, we have the value on the stack, and now we perform the push Z. So it means you take the value on top of the stack and put it onto the variable Z. Okay, so you can see that this have the multiple instruction compared with the other methods or architectures that have the shorter program. So definitely this one require more execution time compared with the tree address ISA. So we can see that instruction length is affected by the number of operands supported by the ISA, and any instruction set, not all the instructions require the same number of operands, and the operation that require no operands, such as the haunt, necessarily waste some space when fixed length instructions are used. So one of the way we the designer can use that to recover some of the space is to use the expanding opcodes. So basically the expanding opcodes that represent a compromise between the need for a rich set of opcodes and also the desire to have a short opcode and just a short instruction. We can see different ways to use the expanding opcode in a next video.